Hello, everyone, and welcome to Lesson 4.2, Part 2, completing the square, and we're going to talk about some application problems in this video. Now, a few things about, the last video and what this video is about and things like that. Number one, if you're watching this video and it is October 22nd, 2024, that's 10/22/2024. If you're watching this in my third or fourth period class, go ahead and start on the homework, yeah? Go ahead and start on homework 4.2 because all you need to do for that homework is the last video. This video is the part I really wish I was in class for to explain in person and things like that. This video actually falls a little bit more in line with lesson 4.5. Now, the practice we're going to do in this, you'd still want to do before that lesson because that one's going to have a lot more stuff involved because we're going to have much more math under our belt. But this is kind of our first exposure to application problems and how to use completing the square to basically solve real-world application problems. But some of these are a little difficult, I'll admit. Some of them, they're really, that's why I'm kind of going through this, making a video for it. That's why we talk about it in class, because there's going to be some interesting creative leaps that we do, and it's not so much the math that's used to solve the function, but more so the math used to set it up. And so in this video, we're going to talk about min and max, which is optimization. Yeah, so getting into the video now, we're talking about parabolas, right? Parabolas look like this or like this, who either have a minimum or a maximum, right? And so when we say optimization, you're usually trying to maximize something, right? So here's an example. If you've seen the Golden Gate Bridge, right? Kind of looks like this. Let me do that a little bit better. Something like this. You've been to San Francisco, perhaps? I don't know, maybe you haven't. I have, actually, a few times. There it is, and then here's Alcatraz, right? The jail, Alcatraz, right? And here's the freezing water with the sharks. And then here's Godzilla, because he attacks. And then here's a monkey. Sorry. I'm thinking Planet of the Apes. I'm not going to draw a monkey. I'm being silly. Let's get over and actually think about. So if you've seen the Golden Gate Bridge, you might have a minimum height above the street level, right? Because this is the Golden Gate Bridge like this, and then this is street level, right? So you're looking at the minimum of something. Or maybe there's a profit function where profit is deemed the y-axis, and so you're trying to maximize how much money you can make, right? So that's the theme, is looking at min and max, optimization, things like that, okay? Okay, so let's start with example 1 here. It says Jenny wants to build a fence for a vegetable garden in her backyard. She only has 90 feet of fencing available. It says, what is the maximum square footage possible for the garden? And that is like, what? Okay, I've got 90 feet of fencing available, and the question is, what is the maximum square footage? And there is no hints or indication how in the world I'm supposed to do this. So, here we go. We're going to assume Jenny is building a rectangular fence, okay? So let's build a rectangular fence, something like this. Do I know the width and length of this fence? I said, no, I don't. So I'm going to call one of the lengths X and one of the lengths Y. To just generalize, I don't know what this is, right? Now, it says that Jenny has 90 feet of fencing available. And if I think about, okay, this is a rectangle, and there's really only two things I could maybe figure about this rectangle. I could know its perimeter, Or I could say, what is its area, right? Maybe I'm interested in perimeter, maybe I'm not, right? The question asks for maximum square footage. That's referring to area. So if you think about area is just length times width, right? X times Y. So that's easy enough. Perimeter, well, it says that we have 90 feet of fencing. That's referring to the lengths, right? This plus this plus this plus this. So totally sums to 90. So that's those measurements. So if I make an algebraic equation representing perimeter, I'd have 2x plus 2y is 90. And so what you kind of have here, it's sort of like a system of equations. 2x plus 2y is 90, and x times y equals an area. But really, the goal is to solve for area, not x or y. I mean, maybe along the way we'll find the x and y that makes a maximum area, but we don't know that yet, right? We're trying to find a. So it's kind of like a system of equations. So what are you supposed to do here? And how is this related to parabolas, right? I don't see anything squared here. So here's how this problem is sort of tackled, and this is a really good type of problem that you might encounter in calculus, yeah? Because it's using really advanced algebraic thinking. The math itself is not hard. It's the thinking behind it. It's setting it up. So we're looking for optimizing area. And I've told you that the theme of this unit is quadratic. So we're seeking to turn A into sort of a quadratic function, because if we could do that, we could find a maximum area, right? So, well, how are we going to do that? Well, you see that equation 2x plus 2y equals 90? What if you solve for y? Look, 2x plus 2y is 90. Let's isolate y by subtracting 2x from both sides and then dividing by 2. Then I get y equals 45, because that's 90 divided by 2, minus 2x over 2 is just x. So this says y is 45 minus x. But wait a minute. Area was x times y, and y could be represented as 45 minus x if you put it in terms of x. Now this is interesting. Distribute the x. You get 45x minus x times x is x squared. Hey, that's a quadratic, right? That's an x squared term, which makes a parabola. Well, not really a sideways, but like this, right? And so the goal now is to essentially maximize that parabola. So I'm going to erase some of this information. I don't really need this anymore. I don't need any of this, none of that, none of that. All I need is the fact that area is 45x minus x squared. And I say, well, how am I going to maximize this? Well, if you had so this is in standard form, right? Ax squared plus bx plus c. Well, what you could do is you could rewrite this with the x squared in front. You say negative x squared plus 45x. And this is in standard form. What if I had it in vertex form? Because if I had it in vertex form, which looks like this, h comma k, h comma k would tell me what the vertex is. And if I wanted to know the maximum area, then I would want to know k, right? And so that's what essentially the goal is. So completing the square, the skill we learned from the last video, we're going to do that and find k. So, okay. How do I do this? Well, first of all, when you complete the square, the lead coefficient, which is right now negative, right? That needs to be a positive 1. So a little tricky here. You got to factor out a negative and say x squared minus 45x. Okay, beautiful. Once you've done that, well, now you have to complete the square, right? And completing the square, that's that little jingle. Say a little melody. right? You take the B guy, divide him by 2, then square it, right? And so you say, okay, what I'm going to do is I'm going to take negative 45, the B guy, divide him by 2, and square it, yeah? So what does that come out to be? I said, well, you've got to square it, and I don't really want you to use a calculator. So negative 45 times negative 45, that's just 45 squared, and 2 squared is 4. But I need to know 45 times itself, so let's just do that multiplication. 5, 2, 22, 2, 2, 0, 16, 18, 5, 2, 0, 1. There it is, 2025. So you say, hey, wait, 2025, that's next year, 2025. Because this video was recorded in 2024. So it's 2025 over 4. This is the magic number we're going to add to complete the square. So it looks like this, negative x squared minus 45x. And we're going to add inside those parentheses 2025 over 4. I don't care what the decimal is right now. Now, remember, and as we said in the last video, you can't just add something silly, right? You got to make sure it's balanced. Anytime you add 9, you got to minus 9 so that effectively you haven't done anything. Yawn break. Sorry. Sometimes one must yawn. And I happen to do that a lot at home at 9 o'clock at night. Okay. So I've added 2025, right? But I got to balance it. And you would say, oh, well, then let me minus it. Except, well, hold on. You see how that's a minus? The minus distributes to 2025 over 4. Meaning, minus times plus. You have actually subtracted 2025 over 4 from the equation. So in order to keep balance, you must add it. And see, I hope I didn't lose anybody there. You're saying, what? First of all, why are you making me do math with such a terrible fraction? And I say, it's okay. It's not that bad. But see, the minus is distributing to this, so it's really subtraction. So the opposite of that is addition. So that's how you keep it balanced. Now remember, because we're trying to factor this to find vertex form, right? Yeah, you might have to do a little X puzzle with 2025 over 4 and negative 45. You'd say, Mr. Spake hates me. Why did he give me this terrible, terrible number? And I say, well, remember that there's a little shortcut, and that shortcut is when you have a perfect square trinomial, you can just cut the middle term in half, and then boom, you're gone. It's done, right? This becomes this, because perfect square trinomials are of this form, right? 2ab plus b squared. And they always become a plus b squared. So you're just taking this and sort of cutting it in half, okay? Anyway, that's that, and then it's plus 2025 over 4. Ta-da, it's in vertex form. And so you go to, what's her name, Jenny? Okay, you go to Jenny. You say, Jenny, I found vertex form of this equation. And she says, big whoop, what's the maximum square footage, guy? I say, look, Jenny, look. Here's how you can do this. Vertex form tells you the vertex, HK, right? So I know that the vertex is at 45 over 2, comma 2025 over 4. And Jenny says, well, thank you, but what am I supposed to do with that information? I say, well, look, Jenny, the parabola looks like this, right? And the maximum's right here. And so this is h comma k. And the function I made, the x-axis is x, one of the lengths, but the y-axis isn't y, it's a, the area. So this k value is your maximum area. Boom, that guy right there. 2025 over 4. So you'd say, hey, Jenny, your maximum area is 2025 over 4. And she'd say, great, I don't have no idea what that number is. And I'd say, no worries, Jenny. Let's do the little long division, right? 4 goes into 25 times. That's gone. 4 goes into 2 0 times. 24 is 1, so that's a 6. And then you drop the 10, you make it a 10. So it's 8 by putting a 2 here. And then it's 20, and so it goes to 5. Boom, done. Jenny, the maximum area is 506.25. And then you say feet squared because we are good students who put their units on such measurements, right? That is my maximum area. Done. Hooray. And Jenny is happy. Let's give her long hair. Happy Jenny. We've maximized the area of her garden, which is 506.25. Amazing. You'll visit this kind of problem again in calculus, but you'll learn other techniques to do this that aren't completing the square. But this is a neat little way to show you that, hey, you complete the square, you find the maximum area of this potential garden. Who knew, right? A few follow-up questions about this. Yes, we've answered the main question, but just a few follow-ups. It says, what are the dimensions of the garden with maximum area? Right, so if you were to tell Jane, okay, the maximum area you can have is 506.25 feet. And she says, that's great. What length and width do I need to do that? And I say, oh, okay, let me help you out here, right? So the h value, that's like the x, right? We saw this in terms of x. So what this tells me is the x length is 45 over 2. Of course, 45 divided by 2, cut that in half, is 22.5 feet. So you'd say, okay, Jenny, look, one of the dimensions is 22.5 feet. What's the other dimension? Well, earlier we said that y was 45 minus x, right? That came from, well, I guess we deleted it. But it was there, yeah? We did say that. And so what you could say is, okay, then 45 minus the x value, which is 22.25. Now, hold on a minute. 45 minus 22, wait a minute. That's also 22.5. So you're saying x is 22.5 feet and y is 22.5 feet. I say, This is interesting, right? This is notable. What is notable about this shape? Well, the side lengths are equal. We're talking about a square. A square. Yeah? Interestingly enough, and this has to actually go with all maximization problems, to maximize a rectangle, if you have a width all the way around, right, all you need is a square. That's how you maximize area. And so this is just interesting because you could do this for any rectangular problem, right? As long as you knew it was a rectangle on all four sides, then you could just say, oh, well, the maximum area is going to happen if it's a square. And this is actually true. This is true. So, part C, knowing that the maximum area occurs when a garden is a square, how could you have done this without all this interesting, beautiful, but, well, kind of hard to follow algebra work, right? Well, it's not that hard to follow, but you know what I mean, right? I said, well, look, if it's a square, the perimeter, right, that was 2x plus 2y, and I had 90 feet of fencing. But if it is a square, then that means x and y are equal side lengths. So perimeter is a square. That's 2x plus 2x is 90, means 4x is 90. So if I divide both sides by 4, x is 90 over 4. But of course, if I do that, 90 divided by 4, 4 goes into 9 twice. That's 10, goes in twice. Oh my gosh, 0.5, right? And you're done. Hey, x is 22.5 feet. Done, right? So I know a 22.5 foot by foot square, square on all sides, that's going to maximize my area. Neat. Cool. And there it is. So that's example 1. We're going to proceed now to example 2. This is a difficult problem, right? Having to sort of use systems of equations, this idea of creating an area function, and then once you have that area function, completing the square to find what the maximum area is, right? Again, this is more in line with the material we're going to do in 4.5, okay? But it's still useful information for our purposes. Okay, example 2. It says, Gary is selling tickets for a dolphin watching boat tour on South Padre. Oh, I remember making this problem last year because I was going to South Padre Island to watch dolphins. And I did see some. It was actually kind of cool. And it was, you know what? It wasn't that expensive, I guess. I think it was worth the money to go see the dolphins go, you know, it was neat. I didn't get to pet them though, so whatever. But they did bring sea critters aboard. And I did get to touch it looked like this. It wasn't a stingray. It was something else. I don't know what it was. I don't know what it was. Anyway, a skate? Is that what it was? A skate? Okay, anyway. I'm getting off topic here. Again, Gary is selling tickets for a dolphin watching boat tour on South Padre Island. It says he charges $30 per ticket. He will sell 50 tickets. For every $1 decrease in price, 5 more tourists will join the excursion. What then is the ideal price that Gary should sell his tickets for, and what is his maximum possible revenue? This is kind of a challenging question. Okay? This type of question is really common in, I believe they call it business algebra. I'm trying to remember. There's college algebra, but then there's like financial algebra. So if you go into college and you become a business major or accounting major, finance, marketing, whatever, they usually make you take business math classes. And the 2 ones you do are the algebra class and the calculus class. And both classes have problems just like this, right? Where we make what's called a revenue function. So we want to maximize revenue. And since, think about it, we're talking about quadratics. So essentially what I want here is a revenue function that's, well, a quadratic that looks like this so I can maximize price. Now, the hint given says that revenue is calculated by multiplying the price of the tickets times the number of tickets sold. So let's actually write this down. Revenue, this is equal to, let's say, the price of the ticket, how much it costs, times the number of tickets sold. And so how are we going to do this? Well, it says that he charges $30 per ticket. And if he does that, he'll sell 50 tickets. So for example, the revenue he would make if he sold $30 per ticket, he would make 50 tickets. He would sell 50 tickets. So that would be $1,500, right? 30 times 50, this is how much he would make. But then if he sold 29, if he priced his tickets at $29, then 55 people would come. Because what, Mr. Spake? Why? I say, look, because for every dollar decrease in price, if I take 30 and make it 29, then 5 more tourists join the excursion. So once the price is now $29, 55 tourists will join. And so, okay, I could compare. I'm just gonna, do I have a calculator? Oh heavens. I'm looking around. Well, I guess I'm technically holding one. Let's just do 22 times 5. Hello, Desmos. 29 times 55. 1595, right? So this would be 1595. And of course, if I did 28 and 60, I just don't want to do this by hand. 28 times 60, I get 1680, right? So you can see 1680, right? Okay, the price is going up even though I'm decreasing the price of the ticket, right? So the price of the ticket's going down, but the number of guests attending is going up. But eventually, if I sell the ticket for dirt cheap, even if a bunch of people come, it's not going to be worth a lot, right? And so the question is, what is the ideal price to sell that ticket so I get as many people as I can while keeping the ticket expensive enough to keep a profit, right? To maximize revenue. And so here's how this is done. I said, well, if you notice, there's actually some good insight in that math I was just drawing. 50 times, it was 30, right? $30 times 50 people. $29 times 55 people. $28 times 60 people. So if you're thinking about the profit function, or the revenue function, it says the price of the ticket. Well, look at what's sort of happening here. This is going by -1 every time, right? And so let's say that the price of the ticket starts at $30, and I'm going to take off X many dollars, right? Where X is going to be an integer, because I only want to take off $1 or $2 or $3. I don't want to take off like $2.50, right? And then the number of tickets is going to increase by 5 every time. So there's going to be 50 people originally, but for every $1 down, 5 more people come. So it's going to look like this, right? So you might be having a hard time wrapping your head around it. It says, look, the price of the ticket, this is $30 when there's 50 people. If I decrease it by 1, then 5 more people will show up, right? That's essentially what this says. And lo and behold, look what you've created, a quadratic, yeah? You've made a quadratic. So what you can do with this is a revenue function. This is basically in factored form, right? Well, it's not just basically. It is in factored form. And we could put it in standard form by using distribution. So 30 times 50 is 1,500. 30 times 5 is 150x. And then negative x times 50 is minus 50x. And then negative x times 5x is negative 5x squared. So let's rearrange that. That's negative 5x squared. This combines to be 100x and then plus 1,500. All righty. We're getting somewhere now, right? The hard part is done. This is what actually makes this problem so difficult, is figuring out what the heck quadratic actually models revenue, right? But it's the price of the ticket times the number of tickets, and these two equations help model that. Okay, knowing this, we want to maximize revenue and tell Gary what he should sell his tickets at, right? So the way we're going to do it is like this. So you've got negative 5x squared, was it plus 100x? Plus 100x plus 1,500. We got to complete the square on this to put it in vertex form to know the maximum. But you can't complete the square unless the lead coefficient is 1. So we got to factor out negative 5. Looks like this. Factor out negative 5, you get x squared minus 20x minus, is that 300? Yeah. Okay. So just if you got to pause, take a look at it, figure out how we got this. I'm going to go ahead and move on now. So factoring out this, now we complete the square. Wait a minute, guys. Wait a minute. Silly me. Remember when you complete the square? Oh, I'm so silly. This is hilarious. You say LOL. LOL, Mr. Spake. You did it wrong. Remember, when you complete the square, you don't need to factor out the a value from this. Remember, it's just ax squared plus bx, right? you just factor the a out from that. The plus c is unaffected. So apologies, I shouldn't have done that. Okay, now let's erase this. So to complete the square, you take the b guy, right? You take the b guy, divide him by 2, then square it. Now the b guy in this instance is negative 20, so negative 20 over 2 squared. Negative 20 over 2, that's negative 10, and negative 10 squared is 100. Yippee! So this is plus 100, and then I must keep it balanced, right? So that's plus 100. This is negative 5 times 100. So what I've effectively done is I've introduced negative 5 times 100 to the equation, means I've subtracted 500. To keep it balanced, I have to add 500 so that it makes that fact that I've added 0. So I will say plus 500 right there to keep this equation balanced. And now, if I do my little shortcut, perfect square trinomial, you can just cut the middle term in half. Negative 20 over 2 is negative 10. X minus 10 squared plus 1,500 plus 500, 2,000. There it is. Yay! So we have vertex form, but of course, what is his name? Greg? Actually, I think it was Gary. What is his name? Gary, right? You say, Gary, what do we do with this? I said, well, look, the vertex is at 10, 2,000. The 2,000 is your max revenue. Okay? So I do know the answer to this question. The max revenue is $2,000. Okay? But then Gary would ask, that's awesome, Mr. Spake. I know that I can make $2,000 off these people. How much do I sell it for to do that? Right? Because that's what Gary would want to know. Thank you for telling me how much money I could make. What do I need to price the ticket at to make that happen? And I said, well, X was 10. So then Gary say, oh, okay, price it at $10. And I say, no, hold on, Gary. Remember, X was the dollar decrease, right? What we found that when X is 10, that maximizes profit, but the price of the ticket, right, was given, I'm going to do this in blue, the price of the ticket was given by 30 minus X. So the price is going to be 30 minus X, where X is 10. 30 minus 10 gets me $20. Okay? So, Gary, your max revenue will happen at $2,000 when tickets, well, that's not how you spell ticket, when tickets are $20 each. Boom. And so now you can tell Gary that's how he maximizes revenue. Yeah? And again, these are the types of problems that in those college math classes focused around accounting, business, things like that, this is the kind of math they do in those classes. Will you need that for your major, really? I don't know. It kind of depends. But that is the requirements there. Yeah, so hey, if you're going in, you get some useful practice out of this, right? Plus it builds our understanding, math is actually useful for other things, not just for its own sake, right? Also, you could see 30 minus x, 50 plus 5x. Why don't we go ahead and graph that? 30 minus x and 50 plus 5ax. Whoa, big boy. Hey, look at that. The maximum is at 10, 2,000, just like we found algebraically. Yeah? So I know that that's the ideal price. And see, because if I go along this, if I charge less or more, right, I won't make as much money. Isn't that neat? I think it's actually pretty cool. I would say this is supposed to be sunglasses. Some shades there. I would say that's pretty cool. The little wave. Okay. Last example for the video. This is example 3. Before I proceed, I'm going to take a sip of my Dr. Pepper, because I actually already tried filming this video once, and I don't know. I made some errors, made some mistakes. Let's go Dr. Pepper. And so this is my second time filming it. So I'm taking my time and making sure we have fun with it. Okay. Example 3. Guys, I love this stuff. Oh, this is it just makes me so happy. Is it Mr. Spake? Say, yes, the students, you just gotta love math. You just do. Can everyone taking my class can you just abandon whatever dreams you have and just go, I heart math. Just go with math. It's just so great. Okay, example 3. It says the height of a projectile can be modeled by this function. Oh, you love this. Oh, physics. You go into physics, you're going to do these all the time, right? Projectile is shot through the air. Think about this. Gravity, right? Here's me throwing something. And it travels in an arc like this. Guess what? That arch is a parabola. And it pretty much always is a parabola, unless you have some crazy wind resistance or something, right? This parabolic shape is caused by Earth's gravity, so everything falls parabolically. That's so cool. That's so neat. So it says this equation given here models the height depending on time. Now, guys, this is more abstract, okay? Because it's not position. It's not x, which is distance, and y, which is distance. No. It's t, which is time, and y, or I guess height, h, which is distance. So this axis is going to represent time that the object's flying through the air, and then this will be its height in the air. But regardless, it'll help us find maximum height, okay? So, and I guess this is the first time you guys are seeing this notation. This is read as h of t equals negative 4.9 t squared plus v naught t plus h naught. You might be asking, what is he saying? V sub 0. So whenever you see this, I'm actually going to write V with a little 0 like this. 2 ways you can say it. I guess 3 ways. You could say V sub 0 because that just means it's a subscript with 0. The most common thing to call it would be called V naught. Not, when you know that phrase, all for naught, right? Oh, it was all for naught. Oh, it was all for nothing. Nothing is 0. So you call that V naught, okay? Or you can call it V0. That's probably what lazy engineers are going to do. They're going to say V0 and just be done with it, yeah? So you're going to hear me say V naught. That's what I'm talking about. H naught, same thing. H naught, okay? And whenever you see that little 0, this is context for chemistry and physics. V naught is the initial velocity. Initial meaning beginning, okay? Same thing for H naught, which is the initial height. So when you say initial velocity, that's how fast it's moving the second it's launched. And when we say initial height, that's the height it's launched from. So maybe it's released from the ground, right? Maybe you're on the ground and you shoot something up and it goes up like this, right? Or maybe you're on a platform and then throw something and then it falls down, right? So that's just some general context behind these kind of questions. Okay, let's dive in further. It says, an apple is thrown off the roof of a building 30 meters tall with an initial velocity of 10 meters per second. What is the maximum height the apple will reach? What is the maximum height? And after how many seconds does it reach this height? So, option A says solve the problem using the shortcut equation, boop, to find the vertex, and then round to 3 decimals. So, and this is why I kind of helped you guys see the shortcuts can work. By the way, the shortcuts work on these 2 questions too. The ones we just did, you can use shortcuts there as well. But this problem just specifically asks for it. So here's part A. First of all, we need to build our equation. H of t is negative 4.9 t squared plus v naught t plus h naught. Now, what do I know from the problem? Well, the building is 30 meters tall, and I'm throwing the apple off the roof. So, 30 meters tall is h naught. I have too much red. There's too much red here. Get out of here. Get, scram. Scram, get out of here, if you've seen that video. Yeah. She doesn't like you. Okay, initial velocity is 10 meters per second, so that means v naught, right? So h naught is 30, and v naught is 10. So, my equation is negative 4.9 t squared plus 10t plus 30. Yeah? That is my equation. Option A says, solve the problem using the shortcut equation, x equals negative b over 2a to find the vertex. Okay, so if you remember from class in lesson 4.1, here's how the shortcut works, okay? Time at max height. Right, so this is where the vertex is, right? The x-coordinate of the vertex. Time t can be found by using negative b over 2a. So what I do here is I take the b value, that's this, 10, and the a value, negative 4 points. So that's a and that's b. And I just plug those into my little formula here. Negative b, that's negative 10 over 2a. A is negative 4.9. And so, well, that's just 9.8, right? Negative 10 over 9.8, but double negative. So what I have here is 10 over, it looks like a 6, 10 over 9.8, right? I don't know what that is. I don't know what that is. What I'm going to do now is to find, so whatever this is, let's just go ahead and get a decimal. 10 over 9.8, okay? 10 over 9.8. 1.02. Okay, that's great. That's roughly 1.02 seconds. So what this says is, after 1.02 seconds, the projectile, the apple, will be at its maximum height. Yeah? So right here, the time will be 1.02 seconds. Okay? The height, however, we have to ask, okay, how do we find the height? Well, if you remember from the previous lesson, the way you find the k value, because this is hk, right? The way you find the k value is finding f of h. So what I'm going to do is h of this t value, right here, h of t, that means that's referring to h of 1.02, right? Okay, h of 1.02. Also, be very, very careful, guys. This h refers to height. And remember how I said it's h comma k? Okay, that's not referring to that h. That's just usually what vertex form is, different h, okay? So I say h of 1.02 means negative 4.9 times 1.02 squared plus v naught was 10 times 1.02 plus 30. And so you can type that in a calculator and figure out what it is. So what I'm going to do is Desmos. I'm going to keep the very accurate prediction. So, what was it? Negative 4.9? Okay. I knew that. Come here, you. Play nice. Boop, boop, boop. Negative 4.9. And then this is squared. And then it's plus 10 times 10 over 9.8. I'm using the accurate measurement for time, not rounding, plus 30. And so I get, you can see the calculation right there, 30.102. 35.102 equals 35.102 feet. No, not feet, meters. Meters. Because the question is in meters, right? It's 30 meters tall. So the max height is 35 meters. And I found this by using the shortcut equation. If I was in like a physics class, this is how I would do it. I would just use the shortcut equation and I would be done because it's all calculator work. And physicists, well, they don't really care about math that much, sadly. They should, but they kind of don't. They just care, does it get me my answer? Does it solve the problem? Okay, it works, cool. That's what physicists and engineers want. By the way, if you're wanting to become an engineer, you know how we say that pi is 3.14? It is a bit of a math meme. It's a bit of this is a STEM, science, technology, engineering, mathematics, meme. Engineers just say pi is 3. And they just literally, bridges are built off the fact that pi is 3 and not 3.14159265. Because engineers say, who cares? It's 3. Just a little, if you go down the STEM route and you become an engineer, that's going to be the little meme there, the little joke that they do. Okay, let's look at part B, which is, look, guys, we're basically done with the video. I'm just going to keep on going, though, okay? Part B says, solve the problem completely by hand without using a calculator by completing the square divine vertex form. Express your answer as an exact value, no decimals, no rounding. Then use your calculator to verify this result matches the above, right? What? Mr. Spake, why? And I say, because math is cool and I love math. Okay, h of t is negative 4.9 t squared plus 10t plus 30. By the way, this one's just for fun. This is not on the test. Okay, if you're freaking out, this is not on the test. This is literally for fun. Let's complete the square on this fella. Ooh, look at him. He's so nasty. I say, this is negative 4.9. That's disgusting. That's gross. If you want to complete the square, the lead coefficient has to be positive 1. So you got to factor out negative 4.9 from this expression. Now, that's not so bad for t squared, but you got to factor this out from 10. So what is that? Well, you need a negative times a negative makes a positive. So that's a minus. And then I put 10 over 4.9 here. Look, bear with me. 4.9 times this, the 4.9s cancel and you end up with 10. The negative becomes positive, right? But the 4.9 over 4.9, that cancels. And so we're done with that. Plus 30. But now you need to complete the square, right? So you got to say, okay. You got to take the b guy, divide him by 2, and square it. That means you're taking negative 10 over 4.9 over 2 and squaring it. Heads up, negative 10 over 2. So that's actually going to come out to negative 5 over 4.9 squared. Okay? So that's what I'm going to add. And if I add this, the negative doesn't really matter. So it's plus 5 squared over 4.9 squared. And so I'm actually going to add that right here, plus 5 over 4.9 squared. Actually, that's how I'm going to stick with writing it that way. 5 over 4.9 squared. Now, factor this. Negative 4.9. And don't actually factor it, but take this and cut it in half. Well, if you just do that, we've already done that. It becomes 5 over 4.9. So it's t minus 5 over 4.9 quantity squared. Okay? Plus 30 plus 5 over 4.9 quantity squared. So, okay, what does this tell us? What does this tell us? This right here, 5 over 4.9, that is the time at max height. That's how much time passes so that you're at the maximum height. If you do 5 over 4.9, 5 over 4.9, you get 1.02. Hey, that's what we got right there, right? So complete a square, boom, I got the max time, or I got the time at which the max height occurs, and this guy, 30 plus 5 over 4.9 quantity squared, that's the max height. And if I put that in a calculator, 30, let's do that, 30 plus, parentheses, 5 over 4.9 squared, 31. Hold on, everyone. Is something amiss? Did I ever mistype anything? Because do you see how that match, does it match my my max height answer? Because 31 and 35. I'm pretty sure the 35 one is correct. Am I doing something wrong here? Ha ha ha! Everyone, look. Oh, I love it. Oh, this is why I love math. It's so good. Remember? Oh, I hope you were yelling at me when I made this error. You probably weren't. You probably didn't catch it. Remember how, okay, you got to do this, and then you have to balance it with this? I dropped the ball twice here. Twice. Actually, no. Just once. So, yes, this was minus plus, so this is a plus. That part's true, but the 4.9 distributes to this. So this is missing another 4.9 being multiplied, another 4.9 being multiplied, which actually means the max height. I love that I made this mistake. See, guys, this is what you have to look out for. These are the most common mistakes that happen, even to me. So this is actually 25 over 4.9 squared times 4.9. So one of those cancels. 30 plus 25 over 4.9. That's our max height. And if I get that in a calculator, it looks like this. 25 over 4.9. Boom, there it is. It matches. 35.102. So this is roughly 35.102 feet. Nope, not feet. Silly. Meters. And we're done. And it matches this. And we're checked off. Isn't that nice? That is nice. That is cool. Okay. So that's that. And you're like, woohoo, yay. I want to show just one more thing, and then I'm done with the video. Again, don't worry about this being on the test. It's not, okay? It's just, this is literally just awesome. It's just cool. It's for fun, right? We love fun. Yay. You know how we said, where was it? 10 over 9.8. That was like, right? 10 over 9.8. So, okay, look at that. 10 over 9.8. Okay, what's 9.8 really close to? It's really close to 10. So 10 over 10 is 1. So see how it was just 1.02 seconds? An engineer, it depends. An engineer, a physicist, maybe that 0.02 seconds is life or death, right? Maybe the apple being there at that 200th of a second, I don't know. Maybe someone's going to die because of it. But more than likely, they're just going to say it's 1 second, right? They're not going to say it's 1.02 unless we really, really need that accuracy. So suppose you just said it was 1, then this would be really easy to do by hand, right? You would just do negative 4.9. Where was it? And then you could multiply that by 1 squared plus 10 times 1 plus 30. And so that's, what's that, 40 minus 4.9? Well, that's basically 40 minus 5, which is roughly 35. So see, this is called engineer math because it's lazy. Sorry. I hope no one's parents are engineers and listening to this and think I'm insulting their profession. My dad's an engineer. I'm just kidding. It's just mathematicians and engineers go back and forth about this, right? Yeah, it's 35 feet, right? The max height's 35 feet in the air, and a lot of people are just going to say, look, no, meters. It's 35 meters in the air, so we're done, right? But a mathematician might say, no, preserve the accuracy. It is exactly 35.102, or actually exactly 30 plus 25 over 4.9, right? But anyway, this is all semantics. We're done with the problem. I hope you enjoyed the video. I hope that you are loving math. This is deepening your love and not pushing you away, but actually pulling you closer to all the beautiful things that you can do, right? Maximizing area, maximizing profit, which is pretty cool. And then, physics, engineering, things like that, all right there. So, okay, that does it for this video. Thanks, everyone, for listening, and I'll catch you later. Bye-bye.